Hello everyone and a very warm welcome to my presentation. The title of my paper is Performance Estimation of an Abrasive Water Jet Cutting Process Using Fuzzy Reasoning. Myself is Dr. ASIF IQBAL. I'm currently working as an associate professor at University of Brunei Darussalam, and two of my co-authors are from the same university, Dr. Juliana Zani and Dr. Malik Muhammad Numan. Actually, the paper is about development of a fuzzy rule-based system, which is used for estimation of performance measures in water jet cutting of a commonly used alloy. Motivation of the work. Abrasive water jet cutting is a highly versatile cutting technology that can cut any solid material with plate thickness as much as 150 millimeter. The process performance depends upon the type of the material being cut. Thus, its optimization with respect to the work material is extremely important. It is imperative to predict the quality of the cut surface before the start of the cutting process, especially for thick stock, as a lot of time and energy is invested in the cutting process. Abrasive water jet cutting is highly complex process with multifaceted relationships between predictors and performance measures. Thus, analytical modeling becomes very difficult. So for such a situation, fuzzy reasoning possesses a lot of potential to accurately estimate the performance measures. Thus, based on the motivational points outlined in the previous slide, the objective of the work presented can be stated as to develop a fuzzy rule-based system from the experimental data of an abrasive water jet cutting process and apply it for estimation of the performance measures related to the cut surface quality. Experimental work. This section provides the details in respect of the predictors controlled, the responses measured, and the other fixed parameters. This slide gives the information about the predictors controlled. The first one is the jet pressure. The three levels of this predictor that will be tested are 2500, 3000, and 3500 bars. The second predictor is traverse speed measured in millimeter per minute. And the three levels tested would be 20, 30, and 40 millimeter per minute. The third one is abrasive flow rate measured in grams per minute, which is actually mixed at the last stage of water jet exiting from the nozzle. The two levels tested would be 110 and 220 grams per minute. And finally, the fourth one is the stock thickness. There are two levels of this parameter are 25 millimeter and 40 millimeter. Okay, the performance measures include the list of three measures related to the cut surface quality. The first one is the average arithmetic roughness of the striations free zone, which is represented as RA and measured in microns. The second one is the maximum curve width measured in millimeters. The higher is the curve width, the poorer is the geometrical accuracy, and more is the wastage of material and energy. The third one is the proportion of the area on the cut surface without striations, denoted by PSF and measured in the percentage of the area. Actually, striations is a very rough pattern of the surface, which is consisting of furrows and curved ridges, which makes its surface very poor. And more of the striations are found near the bottom of the cut surface. That is the representative of deformation wear zone, while the upper portion, which is there are no striations, is considered as the cutting wear zone. This slide describes the two kinds of zones observed in the cut surface produced by water jet cutting process. The top one is the cutting wear zone, which is represented by lack of any striations. It's a quite smooth zone. The bottom one, which contains striations, is called as the deformation wear zone. The deformation wear zone is produced at the depths where the kinetic energy of the abrasive particles becomes so low that they are unable to erode the material, but they tend to deform the material over there. So that's why the striations are created in that zone. The fixed parameters are listed in this slide. The work material used is AISI 4340, which is a commonly used high strength, low alloy steel. Its heat treatment is so controlled to obtain the material hardness at the surface equal to 48 HRC. The dimensions in which the rectangular piece is cut has the length of 65 millimeter and width of 55 millimeter, so that the total length of cut becomes 240 millimeter. The abrasive material used in the experiments is garnet at the size of 80 mesh. Average size of particles is 80 mesh. While the nozzle diameter and nozzle standoff distance both are equal to 1 millimeter. Experimental results. This section presents the measurements in respect of the three cut surface related response variables which are described in the previous slide. This slide presents the surface roughness of the striation-free zone. The three plots are presented over here, which are categorized with respect to the jet pressure. The first one is for 2,500 and 3,000, and the third one is for 3,500 bars. The three plots collectively suggest that the high traverse speed yields high surface roughness. On the other hand, the high level of abrasive flow rate yields significantly lower surface roughness, and high jet pressure also improves surface finish, but the effect is just marginally significant. Finally, the stock thickness is found to have no effect at all on the surface roughness. This slide graphically presents the results regarding curve width. The medium level of traverse speed is found to yield the minimum curve width. This is our requirement. Regarding abrasive flow rate, its high level tends to increase the curve width, which is not good. Furthermore, the higher level of jet pressure are found to significantly reduce curve width. And lastly, the high level of stock thickness causes a significant increase in curve width um, due to divergence of the abrasive water jet as it penetrates deeper into the work material. The third slide of this section presents the experimental results regarding proportion of the striations-free area. The higher levels of traverse speed cause mammoth reductions in the proportion, especially at the low and medium levels of jet pressure, which is absolutely not required. The high level of abrasive flow rate tends to increase the proportion, but with the marginal effect. Most importantly, the higher levels of jet pressure have a significant effect in enhancing the proportion of the striations-free zone. And lastly, as expected, a higher stock thickness is likely to have a lower proportion of striations-free zone. The effects of traverse speed and productivity. The experimental results provided in the last three slides have shown that the higher levels of traverse speed do not yield favorable results in respect of the measured performance measures. Nevertheless, the high traverse speed is a key requirement of another important performance metric, the productivity. This metric, productivity, is not measured but precisely calculated, thus it won't be included in fuzzy modeling. The product of traverse speed and stock thickness is a key productivity measure for the abrasive water jet cutting process. So the three levels of traverse speed 20, 30, and 40, and the two levels of stock thickness 25 and 40 millimeter give this product six values, which are tabulated over here, with the lowest one as 500 and the highest one as 1600 millimeters square per minute. This section presents development of fuzzy sets for the predictors and responses, formation of the fuzzy rule base, and its working for parameter estimation. This slide presents fuzzy sets of the predictors controlled in this work. The two predictors, jet pressure and traverse speed, have three members in their respective fuzzy sets, which are named as low, medium, and high, according to their respective values in bars and millimeter per minute, respectively. While the other two predictors, abrasive flow rate and stalk thickness, their respective fuzzy sets have two members each, which are named as low and high. The number of members in the fuzzy sets correspond to the number of levels controlled in the experimental work. These members are evenly distributed in the fuzzy sets. This slide presents the triangular fuzzy sets of the three responses, which are cut surface roughness, curve width, and proportion of striations-free zone. Um, each fuzzy set has five triangular members. The number of members in these sets of responses is kept higher than those of predictors in order to comprehensively cover the scatter distribution of the measured values. The members in all the three sets, which are named as VL, L, M, H, and VH, they respectively stand for very low, low, medium, high, and very high. The five members for each set completely cover the range of the responses measured values. This slide shows the if-then rules of the fuzzy rule base in the tabular form. The first four columns form the antecedent part, whereas the last three form the consequence of the rule base. Based on the exhaustive combination of the members of fuzzy sets of the four predictors, the total of 36 rules are formed. Rule number 11 to rule number 32 are truncated from the table to improve the visibility of the table's content. Um, for each rule, all the members of the four sets are connected by a logical AND. For elucidation, rule number 10 can be read as follows. If the jet pressure is low and traverse speed is high and the abrasive flow rate is low and the stalk thickness is high, then surface roughness is very high and curve width is high and the proportion of striations free zone is very low. Some consequents in the table are including these ampersand signs. This ampersand sign represents the intersection operator that returns the intersection of the two neighboring members of the fuzzy set. Working of fuzzy rule-based system is described in this slide. In the first step, the numeric data comprising the controlled levels of predictors and the measured values of the responses are fuzzified according to the relevant fuzzy sets. In the second step, the relevant fuzzy sets are fired with the varying degrees of impact against the given combination of the four predictors. A single fuzzy value of the response is obtained by aggregating the outputs of all the fired rules using the max-min rules composition approach. In the final step, the resulting fuzzy value of the response is defuzzified to the most appropriate numeric value by using the center of gravity method of defuzzification. The same procedure is repeated for the other two responses as well. In order to validate the predictability of the developed fuzzy rule-based system, additional 10 experiments of water jet cutting process were performed. The new values for jet pressure, traverse speed, and abrasive flow rate were employed. The rule-based system was used to predict the values of the three responses against the 10 combinations of the predictors. The estimated values are compared with the actual measured values of the responses as shown in the table, and the percentage difference for each run was calculated, and average for all the runs was also computed on the right side of the table. The average values of percentage difference for surface roughness, curve width, and proportion of striations free area were found to be around 5, 7, and 12% respectively, as shown in the bottom of the table. This shows that the estimation accuracy of the fuzzy rule-based system is very high in respect of surface roughness and curve width, whereas that of the third response is also acceptable. Finally, two conclusive points can be drawn from the discussion provided. The first one is the performance measures of surface roughness and curve width can be estimated with high levels of accuracy, whereas the third measure, proportion of striations free zone, can be estimated with an acceptable level of accuracy. Secondly, the fuzzy rule-based system can be used to accurately estimate the performance measures of an abrasive water jet cutting process. And thank you very much for your kind attention. I'm ready to answer any questions from the respected audience. Thank you very much.